Hello everyone, my name is Yas Hazouni, and I just want to share with you a neat trick you can do on Excel to optimize your workflow. I call it dynamic interpolation. For example, if you have data with the time as the x-axis, but the readings for the time domain were not taken at regular intervals, um, you can have Excel map your data to uniform time intervals. In the example I want to demonstrate with, I'm showing time versus position, time versus velocity, and time versus acceleration. The time for each of these quantities goes from 0 to 10 seconds, but the interval is not consistent. In addition, we do not have the same number of data points for each quantity. What we want to achieve is to have a uniform time interval for each of the data sets. We can do that by selecting a suitable interval, then having Excel interpolate at that point between the readings available to us. Let's pick 1 second for this exercise. We want to find the position at 1 second. So we have to interpolate between 0.83 seconds and 1.07 seconds. First, we have to find the time reading just before 1 second. We do that using the index match functionality, which is the sophisticated lookup function. We want to find the value in the time column, so the array in the index function corresponds to the value of interest. Then we want to find the position of 1 second in the array of the match function, and we add comma 1 at the end to indicate we want to find the value less than 1 second. We can see that we found 0.83 seconds, which corresponds to the closest value to 1 second, that is less than 1 second. I'm moving the cell to a different location to make it easier for me to work. And I'm fixing the reference of the column by pressing F4 to add dollar signs to the cell's addresses. We want to keep the value we are interpolating at dynamic, so I will not add a dollar sign to the referenced cell. Now I need to find the value in the array just greater than 1 second. We achieve that by copying the equation we already have for the value just less than 1 second and adding 1 to its position in the array. And indeed, we have found 1.07 seconds. We want to find the position reading corresponding to 0.83 seconds. This can be achieved by performing the index match function, by making the index array the position column. We have found 0.86 feet to be the position corresponding to 0.83 seconds. Now we just copy the equation to the cell underneath and have Excel find the position that is one spot after the 0.86 feet in the position array. We found that at 1.07 seconds, the position is 1.83 feet. I'm moving the cells up to make it easier to interpolate. Now I'm just doing the interpolation equation of x equals x1 plus x2 minus x1 divided by t2 minus t1 multiplied by t minus t1, t being 1 second and x being the position at 1 second. We found the position at 1 second equal to 1.55 feet. The tricky part now is to merge all these cells into one cell for convenience. Copying the contents of the index match cells into the interpolation cell does the trick. I'll just speed this up to get to the next step quicker. You can see that I'm using the color-coded feature in Excel to my advantage to make my work easier. And there you have it, a single cell that shows the position at 1 second found using interpolation. This cell references the time column and the position column, and I made sure to fix the formula reference using the dollar signs, which allows me to copy the cell up and down while keeping the time and position arrays locations in the formula unchanged. Now we just need to copy the formula from the position calculation and paste it in the velocity cell. Then we move the referenced arrays to the corresponding time and velocity columns. Then we copy the cell all the way down. And we do the same thing for the acceleration readings. If we want, we can change the time interval, and Excel will update the position, velocity, and acceleration to reflect interpolation at the new time points. I think it will be useful to graph the position, velocity, and acceleration using both the uniform time points and the raw readings we have. On the left, we have the original readings with the x-axis being the time and the y-axis being the magnitude of each quantity. Similarly on the right, but we are showing the interpolated values at regular time intervals. Let's see what happens if we reduce the time interval. The curves appear to be smoother with the shorter time step. And that's it for me. Please reach out if you have any questions.